Welcome to Lecture 3. Today we move deeper into computational thinking by mastering string manipulation and learning powerful problem-solving strategies, guess and check algorithms, approximate solutions, and the bisection method. These are fundamental patterns you'll use to tackle complex problems. Our journey has 4 clear parts. First, we'll learn how to dissect, examine, and manipulate strings of text, a crucial skill. Second, we'll use that skill within loops to implement a brute force strategy called guess and check. Third, we'll refine this to find approximate solutions. Finally, we'll discover a much more efficient strategy, bisection search. We've seen strings as text. It's vital to think of them as sequences of case-sensitive characters. You can compare strings lexicographically, meaning alphabetically, using afach-athi. For example, apple, banana is true. A built-in function you'll use constantly is len. Len ABC returns 3, the number of characters. The length is the count of items in the sequence, and it's the starting point for iterating through any string. To access individual characters, we use indexing with square brackets. This is a critical concept. Indices start at 0. For esta Porsche ABC, S Porsche is A, S Porsche is B. Trying to access S-thresh is an error. It's out of bounds. Python also supports negative indexing. As is the last character, C. Stu is the second to last, B. This is incredibly useful for accessing the end of a string without knowing its exact length. Remember, index 0 is the first, index 1 is the last. Even more powerful is slicing to extract substrings. The syntax is start.stop step. The slice goes from start up to, but not including stop. If you omit step, it defaults to 1. Let's parse examples with s-tash on ABC def. s-shas gives def positions 3.45. S362 gives df positions 3 and 5. Omitting numbers gives defaults. S means 0, len s, copying the whole string. The magic trick, S, one uses a step of 1, perfectly reversing the string. So for 1, 2 goes backwards from index 4 down to, but not including 1, stepping by 2, giving eka. A crucial string property is immutability. Once created, a string's characters cannot be changed. Si, chi, ye causes an error. So how do we modify a string? We create a new one. S uppies ye plus S1 takes the old string S, creates a new string starting with ye concatenated to a slice of the old string from index 1 onward, and then rebinds the variable s to this new object. The old string object is discarded. This is a key pattern. You don't edit strings. You construct new ones from parts of old ones. To process every character in a string, we need repetition. Enter the for loop. Let's recap its mechanics. A for loop has a loop variable that iterates over each item in a sequence. The classic use with range. For var in range, for makes var take on the values 0, 1, 2, 3 sequentially. Range for 6 yields 4, 5. The range function generates a sequence of numbers, but here's the powerful insight. The for loop in Python is a sequence iterator. It can iterate over any sequence, a list, a tuple, and crucially for us, a string. This means you can write for char in hello, and char will become H, then E, L, L, O. This direct iteration is often cleaner than using indices. This slide shows 2 philosophically different approaches to the same task, checking for I or U in a string. The first approach is index-based. We use for index in range len s to generate indices 0, 1, 2, etc. Inside the loop, we access each character as s index. This method gives you explicit control over the position, which is necessary if you need to know where a character is, not just what it is. The second approach is direct iteration, for char in S. Here, char is directly bound to each character. This is more Pythonic, it's clearer, more concise, and directly expresses the intent. Do something with each character. Unless you need the index, this is the preferred style. It reduces cognitive load and potential for off-by-one errors. Let's build a fun practical example that uses these concepts, a robot cheerleader. The program's goal is to generate grammatically correct cheers. The key is knowing whether to use a or an before a letter. We store the letters that need an in a string. An letters, ndas, f-hilmnorsh. Notice it includes both cases. The program flow is this. First, it gets a word from the user and an enthusiasm level. Then it iterates over each char in word. For each character, it checks if char in letters. The in keyword is a beautiful membership test. It returns true if char is found anywhere in the n letters string. If true, it prints something like give me an A, otherwise give me a B. The enthusiasm level could control a loop that repeats the cheer. This example ties together string iteration, membership testing with in, user input, and conditional logic. It's a small project that feels complete and demonstrates real-world string processing. Now we pivot to a universal algorithmic pattern, guess and check or exhaustive enumeration. The mental model is straightforward but powerful. You are faced with a problem where the answer is unknown. You realize you can generate candidate answers systematically. For each candidate, you can definitively test whether it is a correct solution. So you write a loop that generates guesses, tests each one, and stops when it finds a match or runs out of candidates. It's a brute force approach. It's not always clever, but it has a great virtue: simplicity and certainty. If the solution exists within your search space, this method will find it. It's often the first approach you should try when solving a new problem, as it helps you understand the problem structure before optimizing. Here's a canonical example: finding the integer cube root of a perfect cube. For cube -8, we guess every integer from 0 up to 8 inclusive. For guess in range, cube was 1, sets up that iteration. Inside we check if guess 3a cube. When guess is 0, 0 by 3 is 0, not 8. Next, guess 1, 1 is not 8. Guess 2, 2 by 3 is 8. Condition true. We print the result and could break out of the loop. This works perfectly for this specific case, but immediately we see its flaws. What if cube is 9? It will check 0.1, 2, 3. Up to 9, never find a match, and silently end. What if cube is 8? Range 8 plus 1 doesn't make sense here. This simple code is a good first draft, but not robust. It's our starting point. Let's engineer a robust solution. This version handles negatives and non-perfect cubes. The first clever move: we work with abs cube, the absolute value. We iterate for guess in range, abs cube, pa1. The second key insight: we can stop early. If guess through hasu abs cube, break. Once the cube of our guess meets or exceeds the target magnitude, further guesses are pointless. The loop ends. Now after the loop, we must diagnose why it ended. Did we find a perfect cube? We check if guess tree, ABS cube. If they're not equal, we exited because we exceeded the target without ever hitting it perfectly. So we print that it's not a perfect cube. If they are equal, we found a perfect integer root for the magnitude, but we must now restore the sign. If cube 0, guess ash, guess. The cube root of 8 is 2. Finally, we print. Notice the print statement uses string concatenation with stir to combine numbers and text. This code is a small masterpiece of logical reasoning and defensive programming. It anticipates multiple cases and handles them cleanly. The real world is messy. Often there is no perfect integer solution. We need an approximate answer within a tolerable margin of error. How do we find the cube root of 10? We can't enumerate all real numbers. They're infinite. So we use incremental approximation. We start with a guess of 0. We increment by a very small value, say epsilon or 0.01. We check, is guess 3 cube epsilon? The vertical bars mean absolute value. If the difference is less than our tolerance epsilon, we stop. Our guess is close enough. If not, we increment guess and try again. Here lies the trade-off. A smaller epsilon yields higher accuracy but requires more steps and more computation time. A larger epsilon gives a faster, coarser answer. Choosing epsilon is about balancing precision needs with computational resources. This method is still guess and check, but over a continuous space with a good enough termination condition. Stepping by a tiny epsilon is still slow. Can we be smarter? Imagine playing a Guess My Number game where the number is between 1 and 100. The optimal strategy is not to guess 1, 2, 3, but to guess 50. Too high? Now your number is in 1 to 49. Guess 25. Too low? Number is in 26 to 49. Guess 38. This is bisection search. You maintain a search interval, low, high. Your guess is the midpoint, low plus high, 2. Based on the result, you discard half of the interval. This halving happens every single guess. It's breathtakingly efficient. For our cube root problem, if we know the root lies between low and high, we can apply the same logic. It requires that the function f guess atlas guess 3 is monotonic, consistently increasing so that checking guess 3 cube reliably tells us if our guess is too high. Why is bisection so powerful? Logarithmic convergence. If your initial search space has size n, after one guess, it's n2. After 2, n4. After k guesses, it's n2k. We solve for when this is small, n2k1. Why? For x1, the cube root is between 0 and x. But if x is between 0 and 1, say 0.125, its cube root, 0.5, is actually larger than x itself. Our initial search space of 0x would never contain the answer. Similarly, for negative cubes, we must adjust the logic because the cube of a negative is negative. These are the edge cases that separate a working demo from robust code. Your task is to modify it to handle these. So the fix for 0x1 is to intelligently set the initial search bounds. We need a general rule. For the cube root, we can set low prazaur min x1 and high azaur max x1. If x is 0.5, then low 0.5, high 1. The cube root of 0.5, tau 0.7937, lies within that interval. If x is 8, low 1, high 8, and it still works. This simple min-max logic elegantly sets the stage for bisection. Handling negatives requires checking the sign at the start and working with absolute values, then reapplying the sign at the end, similar to our robust guess and check. This process of generalization is where you deepen your understanding of both the problem and the algorithm.